Good afternoon. Today we are going to start a unit about congruent triangles. This is the first of several units involving triangles, so know them, love them, and be prepared to spend some time with them. We're going to start off today mostly reviewing information that you've had periodically through your career as a student. So let's jump right in. The first thing we're going to do, and you don't have to do this, you can if you're infinitely curious. The first thing we're going to do is in classes, we're going to do a little exploratory experiment. And what I ask everyone to do is to just cut out a triangle. And then with your triangle, label the vertices of the triangle. Then carefully tear off the vertices of your triangle. My little squiggles here represent the tear marks. Don't throw them away. You want to keep your vertices. And then see if you can arrange the vertices along a straight line such that the actual tips, the actual vertex of the triangle, so that all three of those vertices are together at a single central point. And just see what you come up with. Go ahead and pause your video if you'd like to do this. Try it, and then join us. All right, if you did this experiment, then hopefully you came out with a picture that looked something like this. And hopefully you noticed that all the vertices of your triangle can be arranged so that they make a straight angle or a line. And from that, you might conclude that all of the angles inside a triangle add up to 180 degrees. That would be the correct conclusion. We'll formalize that later, but for now, just know that all angles of a triangle add up to 180. We just proved it. We're going to do another one of these. So if you can grab another triangle, that would be fantastic. I want you to do the exact same thing that we did up above. Go ahead and label the vertices of your triangle and then tear them off. But actually, I only want you to tear 2 of the 3. The third, please leave intact. And then if you can, go ahead and glue that triangle down somewhere or place it in a stationary place and see if you can draw the exterior angle by just extending the bottom of the triangle or extending the side, one of the sides, and it could be either one, where of the angle that is not actually torn off. And then in this case, what I'd love for you to do is arrange these 2 torn pieces so that the vertice of each of them snugly fits inside that exterior angle. Go ahead and pause your video and try that. Okay, my hope is that in doing that, you discovered that angle 1 and angle 2 perfectly fill that exterior angle space. And I didn't write my conclusions down here, but that is what I hope you found. And if I were given 2 interior angles of a triangle, how can I find the measure of the third angle? Well, I just add them up. The exterior angle is equal to these 2 when added. And if I wanted to, I could take my exterior angle, subtract from 180, because we know that those are a linear pair and straight angles measure 180 degrees. Or I could do 180 minus angle 1 and minus angle 2. Those are all just different ways of finding a third angle when you're given the measure of 2 of the angles. Pretty advanced stuff, don't you think? All right, let's do something else. All right, this lesson today is going to be full of lots of vocabulary, not a lot of really strenuous math, but the vocabulary, much like it was with parallel lines, is exceptionally important. And there's lots of trivial little details that are going to frustrate you, perhaps, because you may find them to be completely ridiculous, but I promise you that there is a reason we harp on them. The first thing I wanted to touch on is just what is a triangle? And technically, even though we've all learned about triangles when we were like 3, technically a triangle is a plainclothes figure created by 3 segments joined at 3 non-collinear points. Look at that. See, you would never have been able to do that as a small child because you wouldn't have known what non-collinear is. Triangles have segments that comprise their sides, and they have vertices that make up the points of the triangle. There are kinds of triangles that can be described using the measure of their sides. I'm sure you're familiar with these. A scalene triangle has no congruent sides. Isosceles has 2 congruent sides. The third side, regardless of where it's located in the triangle, is called the base. And then finally, you can have an equilateral triangle where all sides are congruent. So let's just look at a particular triangle. This is triangle PRQ. And in triangle PRQ, there are 3 vertices, P, Q, and R. There are 3 sides. I listed them there. I like color, so I identify everything with color. You don't have to. That's just my jam. And then there are 3 angles that are created by the vertices and the side segments. And these are my 3 angles. Pretty straightforward stuff. Additionally, as you all know, you can classify triangles by their sides. And as well, I gave you the answers, didn't I? That's pretty cool. Let's see. All right, well, it's kind of silly for me to give you the answers before I actually give you a chance to figure this out yourself, but sometimes your teacher can be a spaz. If I were asked to categorize this, because it has the same kind of congruency mark on all 3 sides, that indicates that this is an equilateral triangle. All sides are exactly the same. You'll notice here that each triangle or each side of this triangle has a different marking. That indicates that all 3 of the sides are different. And this then would be the isosceles triangle. 2 sides are congruent with just 1 mark on them, but the third side, the base side, has 2 markings on it, and that's how we differentiate it from an equilateral triangle. Remember, folks, pictures lie, so you can't always make judgments or conclusions based on the way a picture looks. You must always use the evidence that is provided for you. All right. As promised, here is the formalization of that investigation we did on the first page in the first Explore. And this is the triangle sum theorem. We will use this when we start doing triangle proofs. The triangle sum theorem tells us that the sum of the interior angles of a triangle are 180 degrees. Nothing too revolutionary there. And then as we move on, we remember that we can classify triangles using their angle measures in addition to just their side measures. So triangles basically have 2 names based on their sides and a different name based on their angles. Hopefully you're familiar with all of these. An acute triangle has all angles measuring less than 90. An obtuse triangle has 1 angle measuring greater than 90. A right triangle has an angle measuring exactly 90 degrees. And finally, an equiangular triangle is a triangle that has all sides or all angles congruent. And if they're all congruent and they add up to 180, then each measure is 60 degrees. All right, like I said, lots of vocabulary. I don't think any of that is information that you haven't seen before, but just in case it is, it's good to review. Here again, we are classifying some different triangles just so you can see what they look like. This is equiangular. All angles measure 60 degrees and they're all congruent. All of these angles are less than 90, making it an acute triangle. This triangle has 1 angle that is greater than 90, therefore it's obtuse. And this one is a right triangle. I caution you here, always verify that there is a right angle indicator in the picture, as the little box is what that is, and I highlighted it red for emphasis, or you must be given a measure of that angle as 90 degrees. Never assume because the triangle looks like it's a 90-degree angle that it actually is. All right, so here are some different problems that we can solve using these classifications and theorems. Okay, given what we already know, we can do some rudimentary problems. In this particular example, it's asking me to find the measure of each angle in triangle RST. So what I'm going to do is I'm going to start with the triangle sum theorem. and I'm going to set up an equation because I know all angles of a triangle add up to 180. From there, I'm going to combine like terms. I'm going to use the subtraction property, and then I'm going to finalize with the division property. And from doing that, I algebraically prove that x equals 28 degrees. So if x equals 28 degrees, I automatically know that angle S is 28 degrees. I substitute 28 in for x, and I can find the measure of angle T and the measure of angle R fairly quickly. We could do problems like this for weeks. The next one has a triangle over here. Again, triangle RST. And in this one, I notice all the angles are equal. They're all the same. They're congruent. They're each equal to x. This is basically a proof of what we said about equiangular triangles. Using the triangle sum theorem, I can add the three angles up and set it equal to 180. And again, combine like terms, use the division property, and I conclude that each angle of an equiangular triangle is 60 degrees. The next example has us look at triangle JKL. First thing I notice is triangle JKL is a right triangle. And I know that because this lovely little box tells me that this is a right angle. So angle K measures 90 degrees. I can use my triangle sum theorem again. I can add angle J, angle L, and angle K, set them equal to 180 degrees. Then I can do some substitution because I know algebraically what those angle measures are, combine like terms, subtract, and then use the division property. And I conclude that the measure of x, or not measure of x is not an angle, variable x is equal to 17. Notice there are some differences here. In this one, we were asked to find the value of a variable. In example 4, we were actually asked to find the angle measures. Always a good idea to double check and make sure, unlike me, that you know what the question is asking. So example 6 brings up a great theorem that I love using. I don't know that everyone uses it, but I use this one frequently. It's the corollary to the triangle sum theorem, and it's darn helpful. It says that the acute angles of a right triangle are complementary. Remember, complementary means that they together have a sum of 90 degrees. So rather than going through the triangle sum theorem every time I am faced with a problem that involves a right triangle, I just remember that J and L will always add up to 90 degrees. And I circumvent and avoid having to always subtract the right angle from my 180 degrees. It's just a shortcut if you would like to use it. And then the last theorem that we're going to talk about is the exterior angle theorem. And this is when we did the second exploratory activity at the beginning of the lesson. This is what we basically were able to prove using triangles. And that is that the measure of the exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. And this is important. The two non-adjacent interior angles. So what does that look like? Well, let's look at this example. This example uses triangle DEF. I'm given the measure of the two non-adjacent angles, and I'm asked to find the measure of angle 1. So I can use my exterior angle theorem, which says that angle 1 is going to be equal to the sum of the two non-adjacent, meaning they don't touch angle 1, the non-adjacent angles. I can do some substitution, and then I just combine my like terms, and I learned that the measure of angle 1 is 120 degrees. Now, technically, I could figure the measure of angle DEF by adding these, subtracting from 180, and then once I know the measure of angle DEF, I can subtract it from 180 because angle and angle DEF are a linear pair. This is just a shortcut. It's a little bit more efficient than use triangle sum and linear pairs. Great. As I bumble along with a gazillion papers in 1,000 directions, let's look at another example. In example 8, we are asked to find the measure of angle F. Let's see, where is my picture? There's my picture. Angle F is way up here. We don't know its measure, but we're going to find it. I was given the measure of angle G being 100 degrees, and I was given that angle F to E to H, my exterior angle, is going to be 3 times the measure of angle F. So I'm going to use the external angle theorem. And when I use the external angle theorem and do some substitution, 100 degrees for measure of angle G, measure of angle F, and I know that my exterior angle is 3 times the measure of angle F. I subtract x from both sides using the subtraction property. I use the division property, and I conclude that x equals 50. So angle F is 50 degrees. Pretty cool stuff, huh? Now, that is a crazy simplistic problem. If I wanted to make this a little more complicated, then I could make this quadratic, for instance, and the equation you end up with would be a quadratic equation that you would then have to factor in order to solve. All right, last little bit of knowledge for today is just some information about isosceles triangles. Isosceles triangles have a lot of special properties, so we kind of focus on them just a little bit. In this particular case, I know it's isosceles because for a lot of reasons, I was told it was an isosceles triangle. The 2 legs are congruent, and the non-congruent side is called the base. Angle 2 and angle 3, they are adjacent. The base is between those 2 angles. They are base angles, and that leaves angle 1 opposite the base as being the vertex angle. So that's just some vocabulary for you to know. There are some theorems to know. If 2 sides of a triangle are congruent, then the angle opposite those sides are congruent. Just tells you that the base angles will always be congruent. All right, so this is exceptionally helpful. Just know that when you have an isosceles triangle, the base angles are congruent. That's what it's saying. Darn helpful. There is the converse that also applies. And remember, a converse is just switching the if and the then. And so in this case, it's going to say that if you have 2 angles that are congruent, then the sides opposite will be congruent. 2 angles that are congruent force an isosceles triangle. There is a corollary for equiangular triangles, and we kind of already intuitively know this. If a triangle is equilateral, or it doesn't say if, it says a triangle is equilateral, if and only if it is equiangular. If all the angles are the same, then the sides have to be the same. If all the sides are the same, the angles are the same. So that's all that's really saying. And we've already touched on this. Each angle of an equilateral triangle measures 60 degrees. We proved that actually in one of the examples above. And then the last thing that we're going to ask you to do, and I'm going to cheat a little bit and cover up everything so you don't see the answers right away. And there are a bunch of triangles here. And what I'd love for you to do is pause the video and see if you can find the measure that they are asking. See if you can find the value of x, or the measure of the angles, or the length of the sides, just using the information given. And then check back in once you have completed that. All right, hopefully you were able to do that. And here's just what we're looking at. In this first example, I'm going to use the triangle sum theorem. I know that A is congruent to C by the converse of the isosceles, or actually that is the isosceles triangle theorem because I was given congruent sides, and because the sides are congruent, the base angles are congruent, so they're each going to measure 60 degrees. In this one, I'm going to use the converse of the isosceles theorem that tells me if I have congruent angles, then the sides must be congruent. For this one, again, I was given that it's an equiangular triangle, which means it's also equilateral or vice versa. So I know all the sides are congruent. I set them equal to each other and solve for x. This triangle has lots of different things going on. The first thing I notice is that it's isosceles. The base angles are 60 degrees. Because the base angles are 60 degrees, this third angle will also be 60. So it's an equilateral triangle as well as being isosceles and equal angular. So many characterizations. That I know all my sides are equal. It's asking me to find x. I could set I could set segment ML equal to PL, but that gives me two different variables, which is a system of equations. Yuck. Instead, I'm going to use MP, and I'm going to say that the measure of LP is equal to MP, and I write a simple equation, solve for x. X ends up being 7/4. Do not be afraid if you come up with friendly fractions for your answers. Do not write it as a mixed number. Mixed numbers are middle school. In this case, we would leave it as a simplified improper fraction. And that is it for today, folks. That was a lot of material, lots of review stuff, nothing overly complicated, but it's good base knowledge. And from here, we can do some more interesting things. I look forward to seeing you again.